Now let me apply the third thought process correction tool, abstracting nonlinearity, to the question, how many children per family lead to peace? Let me begin by reminding you of the advice Pogo provided. The future ain't like it used to be. In the past 70 years, many have experienced meteoric rise in well-being. To name a few, flush toilets, electric lights, phones, automobiles, antibiotics, jet planes, integrated circuits, plastic money, bionic parts, and the internet. The middle class has seen a century of impressive improvements, and they're looking forward to some impressive new ones. Cyborg implants to replace those worn-out ears, genetic modifications that undo wayward gene expressions like Tay-Sachs cancer, sickle cell anemia, and nanorobots that will do everything from repair nerves to clean out arteries. Can we keep these improvements going? Why not, the optimists say. If we maintain the infrastructure and apply our capital to new technological projects, we should be able to produce the required goods and services to even a growing community. Optimists believe the disruptions and social conflict that arise from intermittent scarcity have not crippled the advancement of technology. On the contrary, conflict spurs technological advancement. Has anything changed? Is there any reason for these optimistic arguments to grow weaker while more pessimistic arguments grow stronger? Yes. When there were remote and sparsely populated areas on Earth, individuals in constrained regions, for example Europe during the last 1500 years, could move away from their constraints. Don't like the competition in London? Go live in Chicago, where the opportunities to exploit resources are more and the competition is less. What has changed is that most destinations share the same resource base. Oil in Japan comes from the same system as oil in Norway. If there's a scarcity in the system, both places feel it. Moving does not change a thing. While in reality all biological systems are constrained in their growth, we learned, in the richness of our access to energy and technology, constrained growth does not apply to us. Now it is time to get a clear view of constrained growth, for it still applies to us. Its more interesting and influential aspects are about to play a major role in our lives. Believing it does not apply to us is just another manifestation of our limited thought processes. Maybe I should explain the difference between unconstrained and constrained growth. First, let me describe unconstrained growth. You probably know most of what I'm about to say, but the devil is in the details, so I want to repeat it for clarity. Think of a dish with one cell growing in it. A microscopic view of that cell is in the small circle. Each day the cell divides. Each successive day there will be twice as many cells as the day before. Let's make a table of the growth of this bacteria. After 1 day there will be 2 cells. After 2 days there will be 4 cells. After 3 days there will be 8 cells. Who can tell me how many cells will be in the petri dish on the 10th day? My question's rhetorical. I know you know. Let's keep our focus on nonlinearity does not shape our behavior. The answer is about 1,000. After 20 days, there will be about 1,000,000. After 30 days, there will be about 1,000,000,000. Let's plot the data. The y-axis goes 0 to 1,000,000,000. The x-axis goes 0 to 30 days. After 1 day, there are 2 cells. After 2 days, there are 4 cells. After 3 days, 8 cells. After 10 days, about 1,000. After 20 days population, it will be about 1,000,000. Even 1,000,000 is only 1/1000th of a billion. So it's not very far from the x-axis. And after 30 days, the population is 1,000,000,000. Let me throw in a few more points, and it looks like a normal, unconstrained, exponential growth curve. Growth will continue like this as long as the space or nutrients provide no constraints. For example, after 40 days, the number of bacteria will top 1 trillion. You probably got a feel for unconstrained biological growth. Now, I want to introduce the concept of constrained growth. As a first step, let me use a French riddle called the lily pond problem. One day you put a lily in a pond. The lily doubles in size every day. On the 30th day, the pond is completely covered with lily pads. On what day did the lilies cover half the pond? You probably know the answer from Ecology 101, the section on exponential growth. The answer is the 29th day. The lily pond problem is a concocted learning environment. While it makes for an alarming awakening of the meaning of unconstrained exponential growth, and the graph shows the pond half full on the 29th day, there is a difference between unconstrained growth depicted by these red dots and another curve showing real growth with constraints. The constrained growth curve will do a better job of connecting human procreative behavior to social conflict. Let me develop the second curve. Every lily pad that gets food and energy from the sun has a similar propensity to multiply, as shown by the green arrows. However, common sense tells us that two lilies next to each other inhibit the other's growth. Cluster constraints, denoted by the red arrows, slow growth, not only of the surrounded lily, but also of each of the others. Also, as the cluster expands toward the pond's edge, the boundary constraints shown as red arrows begin inhibiting growth. When there is only one lily in the pond, there are no cluster constraints and only the smallest boundary constraints. However, with the creation of the second plant, both kinds of constraints begin increasing. It is obvious that the 1,000 lilies that exist at 10 days create a lot more cluster constraints than do the 8 pads on the 3rd day. In spite of the increasing constraints, the curve still rises rapidly. In fact, the population expands more on each successive day. That is, the number of pads added on day B exceeds the number added the day before on day A. While the constraints do not appear to slow total growth, they do increase the time needed to double the population. That is, in the beginning, the lilies double their population each day, but as the constraint forces grow, the time needed to complete a doubling requires more than a day. Relative to the unconstrained growth curve, each point on the constrained growth curve moves to the right. This increase in doubling time continues until the pond is half full. Then something striking becomes apparent. The population can only double once more. On the 200th day, the lilies will still be a small number from doubling. If the plant's energy to reproduce remains constant, if the birth rate remains constant, how can the population growth slow down? The death rate increases. The constraints have been increasing the death rate since the first lily doubled. The death rate increases until the pond is full, at which time a weaker lily has to die to let the new lily live. These facts produce a curve during the last doubling that is a mirror image of the red dots during the first 29 days. So instead of doing the calculus, I will do what kids do when they do not want to type. They will cut and paste. First, we will create a duplicate of the curve shown. Now we have 2 copies, and then let's move it over to the right. And then we will take the right side and flip it over to the left. And then we will flip the top for the bottom, and then start moving it up to its rightful position. A little bit higher, Now just a little bit up and to the left. Voila, aren't computers fun? I just avoided having to explain the solution to this nasty partial differential equation. Let's look at what the constrained growth curve tells us. You already know the top half of the curve describes the last possible doubling. However, there is more to learn, which ties human procreative behavior to our coming conflict. What comes next is the most important part of the talk. You are about to learn about the crash dynamics of growth within constraints. Now, focus on the forces that create the curve's shape. Constrained forces begin their counterforce to population growth with the first lily. And as the population rises, the force gets bigger and bigger and bigger and bigger and bigger and bigger until the constrained force is so large the population almost stops increasing. Look at the size of the arrows. Look at how they grow larger. Very slow for most of the curve. Then rapidly. As the curve approaches the limit, the constrained forces increase nonlinearly. The same as automobile stopping forces that increase nonlinearly as the stopping distance approaches zero. Just as an understanding of exponential growth explains how a flat curve turns into a steeply rising one, an understanding of the rapidly increasing constraint forces explains how this rapid growth ends so quickly. The end of population growth in a lily pond looks pretty placid. The pond without a sound went through the transition from exponential growth to a family of lilies just replacing its dead with young. Now you know the difference between unconstrained growth and constrained growth. Constrained growth stops growing. For lilies, this end is quite beautiful. Some would say placid. So what does this constrained growth curve and these constraint forces, which describe the lily pond, have to do with human conflict? Humans are not lilies. Their transition from growth to constant population will not be placid. Human consciousness includes a quantitative view of the past, plans, goals, and expectations for the future, capacity to upgrade their technology, create and store supporting resources, and as a result, they can consume above subsistence. This means lilies' consumptive behavior is required for subsistence. Human consumptive behavior above subsistence is elective, and this election is almost unlimited. Imagine the consumptive behavior of pharaohs making pyramids. Lilies obtain their resources from the environment and have no consciousness of their competitors. Humans acquire resources from both the environment and interactions with other humans. For humans, as long as the environment supplies an unlimited amount of resource, for example, air to breathe, the green box, the requirements of two humans for air does not bring them into competition with one another. Thus, the air resource provides few opportunities to generate conflict. But when a resource is limited, like nutrients in a pond, and competitor A or competitor B requires all the resources to survive, competition determines who gets the resources. With lilies living at subsistence, any loss of nutrients in competition means death. Lily A does not know that it killed Lily B, and dead Lily B attempts no retribution on Lily A. But for humans, living far above subsistence, who both eat and sell nutrients obtained from the pond, loss of pond resources to A in competition means B's loss of well-being, not death. Loss of well-being leads to social conflict. Now let's combine this view of human use of resources, loss of well-being, and social conflict with the constrained growth curve. The vertical axis of this graph has been changed from population to the collection of all individual footprints on Earth. The horizontal line is now global carrying capacity. Actually, it's not horizontal. It slopes upward today and could slope downward tomorrow if we run out of oil without finding a suitable replacement. In this region of the curve, when global footprint values are far from the carrying capacity, resources supporting human life are more like the air we breathe. The market price of these resources is capped by the cost of accessing unused resources. However, when the global human footprint approaches the carrying capacity, for example, limits of a fishery, the ever-expansion of fish caught slows. In the time period where the curve goes from steep to near flat, rich consumers bid up the price of fish. In the time period where the curve goes from steep to flat, rich consumers bid up the price of fish. Those living at their financial limits lose access to fish that they previously could afford. Their well-being decreases, and with enough depression in a range of needs, social conflict increases. Throughout history, humans managed the social conflict resulting from scarce resources and loss of well-being. They killed or enslaved competitors. They creatively imposed treaties, laws, and moral codes. They invested in infrastructure and technology with expectations that it would prime the economic pump. And they developed various schemes of wealth redistribution, more recently called social safety nets. Given the rising well-being of even losers of the last century's conflicts, humans have developed a confidence in their mechanisms to limit social conflict. However, these social conflict controls that worked in the past may be like the braking experiences in the blue part of the stopping distance, stopping force curve. Our predictions of their future success from their past successes may be no better than the dashed line predicting stopping forces for the shorter stopping distances, which, if you remember, looked like the points in the red. If social conflicts grow nonlinear, as did stopping forces, and we predict them to grow linearly, we will be repeating the same analysis and behavior errors we made when we did not wear seatbelts and we put out our arms to protect our children. Using linear extrapolation of our past conflict experience and conflict management tools, we are underestimating the magnitude and onset of coming conflicts and overestimating our ability to manage them. Let me use 4 curves to describe in another way our blindness to this coming crisis of conflict. This purple line shows the rise of the average individual's consumption or footprint over time. The bottom of this curve lies along an individual's subsistence consumption. Below this line, people die from insufficient water, food, or shelter. This is the point where hunter and gatherers change to farmers. Before this point, each human consumed what he or she needed to survive each day. After this point, an individual's daily consumption could be any amount. The present is this vertical line. Today, the average human footprint is far above subsistence. Now let me add a second familiar curve, the constrained population growth curve, the one with 8 kids per family and a high death rate due to poor health, starvation, and deadly conflict. The one that has reached 6 billion people. It is a good thing we had constrained growth. With unconstrained growth, if each woman who lived at the time of Christ had only 3 children, not 8, each of whom lived to age 60, then the 6 billion population mark would have been reached 300 years later. The only reason it took 1,700 more years is a huge death rate. The third curve, a green line, is the global carrying capacity. It is not just space per person, but also heat, transportation, recreation, and entertainment. The units of this curve are footprint units. The zero reference for the green carrying capacity line is here. I'm sorry, the carrying capacity line overlaps the population curve. There was just not enough room for the curves on this page without the overlap. The carrying capacity curve is sloped upward as time increases to reflect humankind's creative genius. Projection of the green line into the future assumes we transition to a cheap, clean energy source other than oil. If we don't, then the green curve could be lower than it is now. The fourth curve, a blue line, is the total human footprint curve. It is created by multiplying the per capita consumption at a point in time times the number of people at that time to get the total human footprint at that time. Since the units of the total human footprint curve are the same units of the green carrying capacity curve, the blue curve rises from the same zero line that defines carrying capacity. Remember the lily pads crashing into one another, crashing into the sides of the pond during the last doubling? Well, for humans, as the blue curve approaches the green curve, as the total of all individual footprints collected together approach the carrying capacity, the collisions among these individual footprints increase. The needs of one person for the resources or services currently used by another increases. And as the constraint forces driving these footprint collisions increase nonlinearly to enormous values, so does social conflict. Somewhere near here, the resulting expanding social conflict will hit us like an unexpected car crash. We will know that civilization is broken when half the population of the world, after experiencing enough loss in their well-being, all turn into radical nationalists or religious zombies and come after anyone who has taken or appears to be taking their well-being. It appears that the human community's biggest and possibly its most hidden problem is an imminent crisis of expanding conflict. In the closing section, I will discuss our options.